Okay, today's lesson is on Kepler's laws. So Johannes Kepler was a physicist, and he was sort of famous for making all kinds of random theories and didn't really have the data to back it up. So his logic was, if I make a whole bunch of different random theories, eventually some of them are going to be true. And what happened was he worked for a different scientist named Tycho Brahe, who did lots of astronomy observations. And what happened was he had years and years of data and accurate measurements of things in space. And Kepler started working for him and found this data, and then ended up using some of his data to come up with his three laws. So we'll go through today's three laws. Will be on Kepler stuff dealing with orbiting bodies and things in space. So the first one is it's sort of just a basic theory one, where he's saying instead of objects orbiting in a perfect circle, they actually orbit in an ellipse. So when we think of the Earth orbiting the Sun, right, we think of the Sun being in the center, and we have the Earth going around it in a perfect circle. So what Kepler's saying is that's not actually true. What actually happens is we have the Sun at one of the focus points of an ellipse. So you think of an ellipse as sort of being like an oval shape, which we sort of have like two centers almost, and then the Earth orbits around in an oval shape. Okay, so that's what Kepler's first law is. So his first law is, Earth orbits the Sun in an elliptical shape. And this works for any object. So it could be the Moon going around the Earth, or man-made satellites, or anything going around Jupiter, or whatever. It doesn't matter. So anything orbiting an object will follow the path of an ellipse instead of a circle. And in the grand scheme of things, they're not much of an ellipse. Like some planets orbit a little bit more elliptical than others. Others are more circular. And it sort of depends on what the planet is and what we're talking about. But you just got to keep in mind that we actually go a little bit of an elliptical path. And that means then when we're doing our calculations, usually when we look at a calculation to give us the radius or the distance from the Earth to the Sun, what that is actually an average, instead of it being, because it sort of changes as we go around the elliptical path. So what we do is we just sort of average it and treat it as if it is indeed circular. Kepler's second law is another theory-based one, and it sort of continues of the oval one. So we assume that our orbiting path is an oval shape. So I'll just sketch that out. So let's suppose we have the Earth going around the Sun again, and it's going to follow some sort of oval pattern. Okay, so what his second law says, that the planet sweeps out equal areas in equal times. So what that means is when the Earth is close to the Sun, and let's suppose it covers a certain distance like that, so let's suppose if we kind of do an imaginary sort of pie shape, that the area from the Earth to the Sun over that course of time is going to be the same in the equal amount of time somewhere else. But what happens is when we're further away, so when the Earth is over here somewhere, to get equal area, it's going to be sort of a longer, skinnier type of pie shape. So what that means is, if these are equal areas and the time are equal, so if the time that it takes to get from there to there is the exact same as the time to get from the smaller end, basically what happens is, with Kepler's second law, is we say that we're covering more distance in the same amount of time when the Earth is close, less distance in the same amount of time when the Earth is far away from the Sun. So what ends up happening is our speeds are different. So when the Earth is orbiting near the Sun, our velocity will be larger. And then over here, our velocity will be smaller. Okay, so that's sort of the key idea to Kepler's second law. Because they go in equal time, but they have different distances, obviously then the velocity is different. So a good way of thinking about it is, imagine the Earth sort of going in orbit. When it gets closer to the Sun, it's going to speed up and kind of get slingshotted around the Sun, so it'll go a little bit quicker. And then when it gets further out, it slows down a little bit. So a lot of people think this is sort of the reason why our winters seem to take longer and our summers tend to be shorter. And that might partly be the case, but basically it doesn't affect our seasons too much. It's more our seasons and our temperature is more affected by the tilt of the Earth away or towards the sun, not just necessarily the distances. But it probably does affect things a little bit as well. Kepler's third law now is the one that we actually do calculations with. And what he said was all objects that are orbiting around the same source will have the same rate or the same constant where period, or period squared, over the radius cubed. Okay, so what he comes up with his formula, we call it Keplers Constant, and it's actually t squared over r cubed. Okay, so what that means is, let's suppose we were talking about the Earth going around the Sun. So the time it takes for the Earth to go around the Sun, the period is, let's do it in days, 365 days. And the distance or the radius from the Earth to the Sun, the average orbit, is 1.49 times 10 to the 11 meters. So we could actually do Kepler's constant to figure out what it is for Earth around the Sun. So if we leave it in days, we get 365 squared over 1.49 to the 11 cubed, and that would be Kepler's constant. So what we end up getting is some sort of weird constant number, but it really doesn't tell us much. What it's just sort of telling us is what is the constant for something orbiting the Sun using the Earth's data as sort of a reference point. So what we do is if we actually solve this, let's actually type this in on our calculator, and if we were to solve this, we get approximately 4 times 10 to the negative 29, and this would be in days squared per meters cubed. Okay, but like I said, the units and the data doesn't really help us all that much, but what it does tell us is, let's suppose we did this exact same constant for Jupiter. So if we do the days of Jupiter's period divided by its radius, we would get the exact same constant. So what that means is the Sun's constant, Kepler's constant for the Sun, is 4 to the negative 29 for any planet going around the Sun. Because all planets are going to be the same, what we're going to use more often is we're going to use Kepler's formula, but we're actually going to do it as a comparison. So we're going to call it planet A, or object A, going around whatever, and then planet B going around the same thing. So in this case, what this formula works for is we're able to compare two things orbiting. As long as we know one, we'll be able to figure out the other. So for example, let's suppose we have, let's suppose it says the orbit, let's do this, let's say how long is Mars period if its radius is 1.52 times the radius of Earth. Okay, so what we're doing is we're sort of comparing Mars to Earth. So let's call object A in this case Earth. So our time for Earth's rotation around the Sun would be 365 days. We square that. We know its radius is what we just used in the last example, but we don't really care what the actual number is. We can actually just plug this in as a ratio. So we know that Mars is 1.52 times as much, so let's just call Earth 1. So the distance from the Earth to the Sun is 1, and then what we do when we do Mars is we put in 1.52. So if the distance is just going to be 1.52 bigger, it doesn't really matter what numbers we use as long as we have the right ratio. And then we know, in this case, then we're looking for what is the time for Mars. So in this case, it's pretty easy calculation. Go 365 squared times 1.52 cubed. divided by 1 cubed, which is just 1 anyway, and then square root our answer. And when we do that, we get a final answer of about 684. So what that means is, on Earth, it takes us 1 year or 365 days to go around the Sun, and on Mars, the time would be 684 days, which would be almost 2 years compared to our Earth time. So this is how we're going to use Kepler's formula the most, is just by sort of doing a comparison to any object going around the same thing. So let's do one more example. So let's suppose in this case we have the moon goes around the sun. So let's suppose the moon's period it's roughly 28 days. We'll just leave it like that. And let's call the radius 1 again. And then let's say we have some other satellite. So let's suppose we have like a TV satellite or something like that. And let's figure out what the period is for that satellite if the radius is 0.25. Okay, so what's happening is, let me just kind of draw a sketch. So we have the Earth here. We have the moon orbiting the Earth. Okay, so what I'm saying is, what would the time it would take for a satellite if it was only a quarter of the distance? So if we have our total distance from moon to the sun, and our satellite is a quarter of the distance away. So we can use Kepler's formula to do this just like we just did. So we'd have t squared over r cubed for each. So we'd put in our 28 days for the moon over, let's call it a 1 radius, and then we'd have time squared over 0.25 cubed for the artificial satellite. So once again, cross multiply and solve, and we'll get a period of 3.5. So that means if the moon takes 28 days to go around the Earth at its location, a satellite that's a quarter of the distance out would only take 3.5 days in comparison. Okay, so just cross multiply 28 squared times 0.25 cubed divided by 1 cubed, and then square your answer. So that's it for Kepler's. You can work on the practice questions on these ones.